It probably won't surprise anyone that when we charge a mobile phone, it's powered by electricity. But did you know that generating electricity isn't that complicated? All you need is a piece of wire and a magnet. However, this way we cannot produce direct current, which is what powers the phone. Instead, we generate what is called alternating current. But alternating current is not a problem. On the contrary, it brings key advantages. That is why this type of current is also found in wall sockets. And that is exactly what this talk will be about: how to generate electricity and why producing alternating current is advantageous. To answer that, we only need one key principle, and that is, when the magnetic field around a conductor changes, an electric voltage is induced in it. We can imagine electric voltage as pressure that pushes electrons through a wire. And this movement of electrons is what we call electric current. This electrical pressure, electric voltage, arises precisely when we change the magnetic field around a conductor. And a change in the magnetic field can be achieved in two ways. The first method, a changing magnetic field. If we have a coil into which we supply a current of changing magnitude, we also create a changing magnetic field. In a second coil, voltage is induced due to this changing field. Depending on the ratio of turns in the first and second coil, we can increase or decrease the output voltage. This is exactly how transformers work, the ones you can find on power lines between a power plant and your home. Transformers significantly reduce the cost of transmitting electrical energy, because the higher the voltage, the more efficient the energy transmission. On the other hand, lower voltage is easier to control and also safer. The second way to change the magnetic field is a moving field. If we have a constant magnetic field, for example, a permanent magnet, and we move the magnet around a conductor, voltage is induced in the conductor. This principle is used by generators and electric motors, and this is exactly how we will try to generate electricity. To create the highest possible voltage with the moving magnet, several factors need to be considered. Firstly, we want the changing magnetic field to affect as much of the conductor as possible. For greater voltage, we want a larger coil, which must be acted upon by a proportionately large magnet. It's also necessary to add more turns to the coil, because each loop contributes to the total voltage. Another factor is the strength of the magnet. A stronger magnet creates a more intense field, which means stronger effect on the coil's conductors, and finally determines the speed of movement. The faster we move the magnet, the faster the magnetic flux changes passing through the coil, and thus higher voltage is induced. This is our latest version of the coil, which we have connected to a voltmeter. And when I quickly move a magnet near the coil, the meter really shows some number. However, with this circuit, we are able to generate so little energy that we can't even light up a simple LED. By applying the principles outlined above, we developed this generator to increase energy output. Using a magnetic field, we will generate voltage in this coil. To allow more magnetic field to pass through the coil, one magnetic pole is composed of 4 magnets with the same orientation. In total, the generator has 14 magnetic poles. We want to create a changing magnetic field, so the orientation of the magnetic poles alternates. To achieve a higher frequency, the generator does have a gearbox. Now let's see whether the LEDs will light up this time. And indeed, the LEDs are shining. So this is how electricity can be generated using a coil and a magnet. But what kind of electricity did we generate? To answer this question, we can use an oscilloscope, a device that displays voltage over time. This allows us to see on the oscilloscope that the voltage does not have a constant value over time. On the contrary, its value changes. At one moment, it is plus 2 volts, and a fraction of a second later, it is minus 2 volts. This is exactly the waveform of alternating voltage. When we have alternating voltage, it pushes on the electrons alternately, and so the current also flows in an alternating manner. Thanks to the oscilloscope, we can also show that when I start turning faster, the voltage magnitude increases. This primitive generator works on the same principle as large generators in power plants, which also produce alternating current. Because alternating current can create a changing magnetic field, we can use transformers to increase or decrease voltage, making energy transmission more efficient or safer as needed. Because the entire system of energy generation and transmission is based on alternating current, the functionality of this system relies on a single principle. Electric voltage is generated when the magnetic field around a conductor changes.